Hi, let's start our new clips on the theory of structure. We are now alive as chapter 7, in which we are going to talk about the defection of the structures, including the beam, the frame, and the truss. The learning objective of this chapter is to let your student to understand and be able to determine the displacement of statically determinate structure, including beams, truss, and frame. What is the displacement? The displacement is the way the structure respond to the force. For example, if we're talking about the beam, when the beam subjected to this kind of loading, you may imagine or you may do the experiment with your ruler that is going to defect somehow like this. Okay, and if you're talking about the frame, you have very simple frame like this. This is the column, this is the beam, and your frame have a fixed support here. Okay, this is going to be rigid support, rigid joints, and then your frame subjected to a force, let's say at the tips of this beam, and you may imagine easily that this frame gonna move to this point. By moving this, that means this frame gonna be defect, okay, like this. And since this is fixed, there is no movement here. And this is rigid joint, so the deflection of the frame gonna be like this. Okay, and if you talking about the truss, the same thing occur. Under the force, the truss also have some kind of displacement. For example, if we have the truss like this and is subjected to very simple force, let's say the force at a point on the truss. Okay, this is a truss. Have the joints that subjected to the force. Okay, when the joint subjected to the force like this, the truss will change its shape or have some displacement. Change the shape, have some displacement. So this joint gonna move like this, and when this joint gonna move like this one also gonna move. Okay, but smaller than this, and this one maybe stay here. So the bottom chord of this truss, let me change this a little bit, supposed to move or displace to be the shape like this. When the bottom chord move, so the top chord also move. Okay, the new shape of the truss may be imagined to be something like this. This is called the displacement. This is called the displacement of the beam, of the frame, and of the truss. And normally, when we talking about displacement, another point is mentioned about how the point move. Okay, how the point move. Move what? Move downward. So usually we call this V in vertical. And also the point may be rotate. So this called theta. Okay, let's say this is A, this is going to be theta sub A. So this called slope. So the displacement contain the slope. This is going to be V at what? At C vertical. This is going to be, slope at A. This is going to be deflection. Deflection. It's going to be vertical deflection at C. Okay, that's it for the beam. For the frame also have what? Have this displacement, and also this displacement. Okay, let's see. This is going to be theta at C. This is B. This is A. And this is going to be V sub C. This one in what? In vertical. And this is going to be V deflection at C in horizontal. So the frame has additional displacement, which is the which is the horizontal displacement. Sometimes we call this horizontal, okay, deflection, okay, at C, or you may call it also like a side sway, okay, side sway of the frame. For the task, the task may have the deflection in vertical and also horizontal. So the task, let's say this is A, this is B, this is C, may have V sub C in horizontal and V sub C in vertical. The task has no slope. Okay, the displacement of the task consider only the joint. It has only movement, only the linear movement, no slope. Okay, and what method we are going to talking about? We are going to talk about various methods, and we are going to go back, review something about this double integration and superposition. These two methods we have them in mechanics of material already, but anyway we're going to revisit it. Okay, and then we're going to talking about two more important methods to determine the deflection. One is the conjugate beam and the moment area. They are very similar. Okay, they have very similar origin, and due to the applicable and easy to use, we are going to take a look more carefully at the conjugate beam. Most of the time, these two methods used to analyze the beam. Okay, mostly we involve with the beam, and we also have another two methods. They also related to each other, and we will concentrate on the virtual work or the unit load method. This method can use to find the displacement or deflection of the beam, of the frame, and of the truss. Okay, and you may see this two also only for the beam. Okay, that is the introduction of this slide. We are going to go into more detail. Let us review the homework first. We will have the homework talking about the deflection of the beam. On the deflection of the beam, I like you to use the conjugate beam to determine the slope, okay, and the maximum deflection of the beam. And for the second, I like you to use the virtual work or the unit load method to determine the slope and the displacement at the end of C. See, you can see the displacement and the deflection. Sometimes they just repeat it also during the course of study. And then come to the task. Okay, the task, you're going to use the method of virtual work or unit load method to compute it. And the last one, this is another one is the frame. That is going to use the method of virtual work to determine the horizontal displacement, only horizontal displacement at the locker B. Okay, and the last one, they asked you to determine only the horizontal displacement at the lower SC by using the unit load method. So mostly here we are concentrated to the conjugate beam and to the method of virtual work or the unit load method. Okay, let's start. For analysis of defection of structure, there are some benefits to do this. The first one, the defection is the basis to analyze statically indeterminate structure that we are going to study in the next chapter. Let's see, for example, if you have the beam like this, okay, and your beam subjected to the force in the middle of its span, you guys can imagine the deflection of this beam easily by using the experiment with your ruler or anything. This is going to be curved, okay, this is going to be curved, and then this part going to be a straight line. This is straight line, this is curved, okay. Why this is curved? This is curved because it's going to subject that to the moment. How about this is straight? Because there is no moment in this portion. This is called statically determinate beam. However, somehow you got to make the structure, for example, strengthening this structure by putting a support to reduce the deflection that occur over here. You may put, for example, you may put the supports as the roller at the end of the beam. Okay. By doing this, the beam gonna change the shape from the previous one to this one. This one still the same, fixed, no zeta and no delta. Okay. Free. We have zeta and delta. Let's see, the delta is equivalent to the deflection. Okay. I will use them across this lecture. It's going to mean the same thing. It's going to mean the vertical or horizontal displacement. And what happened is, since this one cannot move, so this one gonna be here. What happened is the curve here gonna be like this, and now the deflection here gonna be in this shape. Okay, it's going to be downward curve to be the upward curve, and we have this one called the inflection point. Okay, the point, that's the curve change from the concave downward to the concave upward. And this structure is statically indeterminate structure with degree of indeterminacy equal to, this is 3, this is 1, it's going to be 3 plus 1, and we have 3 equations, so we have degree of indeterminacy of 1 degree for this. So we need to have extra equation to solve this beam. Okay, in the next chapter we will use the method, okay, called consistent deformation. We will consider this beam as a new beam like this. This beam gonna subject to what? Subjected to the same force, the same light blue force. But at the end of, let's say this is B, okay, we are going to have the reaction. This reaction is unknown reaction, okay. Anyway, let's put this as this unknown reaction. This is, let's say, it's may call B sub y. B sub y is called the redundant force. Redundant force. Is this unknown? Okay. To solve this, the consistent deformation set, you got to use the principle of superposition to separate this beam into this one and plus this beam into another one. And what we have is the first beam gonna subjected to the real force. Let's say this is 10 kilonewton, this is 2 meter, this is 2 meter, okay. And the other one will subjected to the redundant force. and this is going to be 4 meter. What happened is, under the force, this beam gonna have the same deflection as we have before, curve and then straight line, and this one gonna have the deflection something like this. And the deflection here we may call delta at B. Okay, and deflection here we may call it the what the this one is B sub y, the B sub y time the deflection due to the 1 unit force. Let's call it F deflection at B due to the force at B. And the additional equation we call it the compatibility condition. You know this condition, the compatibility condition before from the mechanics of material when we study chapter 4 about the axial load member and also chapter 5 for the torsional member. What it have is the deflection here is 0 and also here is 0. So it's going to be 0 equal to what? Equal to the deflection here is delta B. Okay, it's a B. We just okay, now we have what? We have the deflection equal to the delta B. So it's going to be delta B here. It's going to be delta B here. And delta B is downward. So it's downward is positive. So if this is downward positive, this is going to be negative. So we're going to have the negative of F sub BB and then times the B sub Y. You can see that this compatibility condition is only based on the deflection of the beam in our consideration. And if you can determine this deflection, you can find the B sub Y. Let's say if B sub Y is like let's say it's a 4.5 kilonewton. If you know this one, 4.5, you know this is 10. So then you can determine the reaction at this fixed support. And then you can draw the shear diagram, you can draw the moment diagram, and eventually you also can determine the deflection of this statically indeterminate beam. Okay, this is the first part. It's a basis for the next chapter, for the higher education we're going to have. Okay, and then the deflection also used to analyze and design of the structure to prevent large deformation. That means we can determine, let's say, the deflection of this beam by the old mechanics of material table. And you can see that if this one is the force of P, this is L over 2, you can determine the Vmax here. That is going to be the maximum deflection. And this is going to be PL divided by 48 EI. If you don't believe me, you can go back to mechanics of material and open the deflection table. Okay, and you also said when you compute it, this is going to be less than L over 360 when your beam have the wall under it. Okay, and if the beam has no wall under it, you may control it at L over 240. Okay, that is the second part of analysis of deflection. Okay, come to the experimental part. Actually, let's ask, has this member, okay, is have the pin here, it have the pin here, it's straight together, and then it has the pin here, and it's straight line. It's a steel rod. Let's say, imagine it is a steel rod, and then it's put to the support. It says pin. When support is pin, what it mean? The pin, the symbol is here. Okay, when the pin support resist the force, okay, the pin support will have both 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 the reaction, okay, that is going to be in the vertical and horizontal deflection. And because the pin support is can allow what? It can allow the rotation, okay. So the pin support delta H equal to 0, delta V equal to 0, okay, but theta won't equal to 0. Why delta H equal to 0? The reason behind is because this has the what? The A, the A sub x, okay, it's a value A sub x. This also have A sub y, but the moment M sub A is 0. You may notice that the deflection are opposite to the reaction. If there is reaction, there is going to have no deformation, okay. If there is no moment, the point gonna rotate. If there is the reaction moment, the rotation gonna be 0. For example, fix it. So this can rotate. And then what you put the force into this steel rod, what happens is the steel rod will deflect or deform or displacement whatsoever you may call it, okay. It's going to be deformed, it's going to be formed like this. Let's say it's going to be formed like this. It's going to be deformed as a curve, and then from one pin to another pin, and the curve have large magnitude, okay, when it's close to the loading area. That is typical, okay, when the structure subjected to force at any point, the structure will deform large, and when it's far away, the deflection going to be less. And there is the deflection that we're going to be interested in. And let me note it again. I may use the V or may use the delta that represent the deflection of the structure, and also the slope. Okay, slope is a rotation. Usually we address that slope at the support. Okay, the frame also. When the frame subjected to the force, the frame deflects. For example, this one, that means the frame gonna deflect actually like this. And for this one, the frame gonna deflect something similar to this. And for the column, the frame also deflect. This is gonna be, okay, this is gonna deflect something like this. And the deflection gonna join each other at the joint. Okay, this also we have the deflection of the structure, and it's going to be deflect, okay, in the shape like this. And you may see what I mentioned, the beam has only what with the vertical deflection and the slope. However, this beam, this frame has what? Has the horizontal displacement, and it also has slope, okay. Actually, it also have very small delta sub V. Oh, sorry, let's call it V sub V. Let's call usually the frame, I like to call it delta more than V. I like the beam. Okay, let me put this like a delta here. It's going to be delta. Okay, delta sub H, delta sub V, and theta. So the frame has one more displacement compared to the beam. Okay, actually the horizontal displacement we call it size 3. Okay, what I'm doing there for the beam and for the frame, I draw what's so called the elastic curve. Okay, elastic curve is what? Elastic curve is the curve that represents the deformation of the structure Okay, deformation of what? Deformation of the actually the centroid, the line that's passing to the centroid of the section of the structure. Maybe the beam, maybe the frame. Okay. So when you put the elastic curve into the diagram, we call it the deflection diagram. So elastic curve mean the curve. Okay. When we put the curve into the diagram, we call it deflection diagram. The benefit of drawing deflection diagram, first one, we understand the deformation of structure under the apply of the load. Let's consider this two beam, and you may try to do your experiment by what? By using your ruler. Okay, and if you do the fix here, this is fixed support. Okay, what is the fixed support? Fixed support, no slope. Okay, and then no displacement, no deflection. The pin allow you to have what? Have theta. When you increase the p, the theta here gonna be increased, and the pin has no deflection. So when you push the beam, okay, by putting this one is a fix, putting this one is the roller, this beam gonna deflect. Actually something like this, and then it's gonna return back, okay, to do this. So this is gonna be concave upward, this is gonna concave downward. Okay, that means you are going to understand. And if you understand this, what happened is you may use this to put the reinforcement. If it's the RC beam, you may put the main reinforcement to the bottom of this first portion because it's concave upward. For the concave downward like this, you may put the reinforcement on the top of the section of the beam. Okay, that means when you understand the structure, you also apply the knowledge into that. Next, let's you consider the overhanging beam. Okay, the next one is called the overhanging beam. For this overhanging beam, what we have is what? What we have is the force gonna push the end of the beam downward. Okay, and you can see the roller allow the rotation as the pin, okay, without the vertical deflection. And also this pin only allow for the deflection. So the beam gonna have the shape like this. Okay, if you cannot imagine, just put the roller and do your experiment. And what we have is this beam always concave downward. That means if you like to do the reinforcement of this beam gonna have the reinforcement that's different from the previous one, or the main reinforcement gonna put on the top. That's still also minor reinforcement. Okay, this is a major reinforcement. That's you to put more to resist the stress, also to reduce the deflection of the structure. Okay, when you understand the deformation of the structure, you may at least able to put the reinforcement onto your reinforced concrete structure. And you also checking the possibility of the calculation deflection. That means it's going to cross check between your moment diagram and also the deflection. What is mean by the moment negative? Moment negative have the meaning that the deflection gonna be concave down, and positive moment, that means this going to be concave upward. Okay, by putting this together, this going to have theta. okay, and the delta is 0. The same thing as the pin and roller. This is theta and delta equal to 0. For the vertical, it can move, okay, upward or downwards, it depends. But by putting this, you should start by this portion, okay, this is gonna move downward. So this guy gonna move and have the deflection upward like this. This is important part. This is 0 moment. The points that change from the upward to the downward concave, okay, curve, and then you have this. And what happened is this second part, it depends on the relative value of the P1 and P2. If the value of P1 is small, if the value of P1 is small, if this is small, let me put it in another color. Let's see. The deflection will be something like this for small value of P1. If the value of P1 is large, okay, if large, it can be something like the same as before, but it may push this one downward like this. So it depends on the value, relative value. If it's large, it's going to put the point A downward, okay. If it's small, the P2 is large, it's going to take the P1 up. Okay, this is what you check for the possibility of your calculate deflection. Okay, and if the real result is shown as picture C, that means what? That means P1 is large for the P2. Okay, and one important thing that I'm going to mention is the inflection point. The inflection point is the point you're going to change the shape of this. And also again, by doing this, what happens is if this one is negative, so that means you're going to put the reinforcement to the bottom part of this beam as shown here. And for this beam, you may put this one on the top because it's subjected to negative moment. Negative moment, put the reinforcement on the top. Positive moment, you put the reinforcement at the bottom. Next, to check validity of calculation of moment diagram. So it's going to go together. Now, how to draw the elastic curve of the beam? You may see Ajahn can draw it easily. I did a lot of drawing of elastic curve from the past. That means I have skill to draw the elastic curve. To develop the skill, there is some subjection. The first one, to draw the elastic curve, the first one, you got to consider the supporting condition. And you may see I mentioned about this for some time already. There is two main things. If the support that resists a force, okay, such as pin, that support will restrict the displacement. I did draw this before. Okay, you have the pin, and then when you have the pin, you have the what? You have the for example, A sub x and A sub y. Okay, so what happened is they're gonna have delta sub h equal to 0 and delta sub v also be 0. And what the pin may have is the slope. Okay, that's the pin may defects over here. And for the other, such as the fixed, if you have the fixed support, the fixed support, that means you're gonna fix everything. You're gonna put everything fixed. Okay, when you put everything fixed, what you mean is over here you prevent the beam, and the fixed support gonna have what? Gonna have the force A sub x, the force A sub y, and also the moment M sub A. So that means delta sub h equal to 0, delta sub v equal to 0, and also theta equal to 0. See? So the second one If the support that resists the moment and the force, that means the fixed support, okay, restriction occur on the slope as well as the displacement. No displacement and no slope for the fixed support. Okay, that means for the fixed support, the location here gonna be stay here, no movement like the pin here. Okay. We have the drawing for the support. The first one is the roller. Okay, you can build the roller support by putting the slot here, and you also may have the pin support for here. You put the detail here so that the behavior of the support is the pin. And then the last one that we have is the fix. To fix the support. Okay, this one gonna have what? Have a sub x, a sub y, and m sub a. So there is no delta h, no delta v, and sorry, it's going to be 0 equal to 0, 0, and 0. Okay, so you are an engineer, you are the one that's going to specify the connection or the joints or the support. So when you specify the joints, the support, you got to detail the structure as you wish. That's very important. Okay, and also later you got to build it as you are decided. And the support, again, the roller have the reaction like this. So only one restriction occur in the vertical direction. Okay, if you change it to the pin have two reaction. So there is two restriction on the displacement. If you change it to the fixed, there is 3 restriction to the fixed. You got to understand this, what happened. It's just in opposite to the reaction. Okay, this one have the x sub x, this one have f sub y, this one have m. Okay, so their relative displacement all are 0. Okay, let us consider very simple structure first. In the drawing of elastic curve, I recommend you, if you cannot understand it, you got to do the experiment by yourself. Okay, this is going to be fixed, so this one won't move. This one is free. What the free is, this one going to move actually downward. Okay, when this one moves downward, what happened is you put your hand in your ruler, and then you can see this one going to be curved like this. And when it's curved, I mean it's curved, it's going to be smooth curve. Okay, the curve going to be smooth. And then if you change from the beam from the top to the beam on the bottom, what is changed is what? The eye change. Okay, this is going to be larger eye. When it have larger eye, this means going to have very small deflection. So it's going to same shape, but this time, this fixed. This time, due to the very strong portion of this AB, okay, the beam will deflect less here because the eye is 1.5 times, so the deflection is going to be 1.5 times less. And then the other one have the same eye, so the deflection for the part BC going to be the same as before. You got to consider the beam carefully. If it have the same eye or it have the change in the eye, you got to respond them carefully. Okay, for this, what happened is this beam have what? This beam has the what? roller here and has the pin here, and then is subjected to the moment. If the structure is subjected to the different moment, what happens is it's going to deform in different manner. For example, this one is going to defect like this. This is plus m moment, and this is going to be negative m moment. Okay, and what we have is look like this and also look like this. So this beam gonna have the shape, okay, in the shape like show here. I show here. Okay, it's going to be have a deflection. Oops, only in the negative. Okay, similar to this. For this one, oh, I forgot to mention about this one have symmetry axis here. So on the left and on the right, it's going to be the same. The same as this one, this beam. This beam have also the symmetric axis here. Okay, due to the equal in the loading. So what happened is this beam going to defect like and have the maximum here. And then the second part gonna copy the first part. It's gonna be here. What happened is this two beam has what? The maximum deflection here may occur over here. That's it's gonna be V max. And also the zeta max is going to occur here. Okay. Due to the symmetry, the V max there and the V max here are gonna be the same. And also the slope there and slope here gonna be zeta max the same. For this one, for the second beam, the maximum deflection going to be here. Okay, that is going to produce V max. However, the zeta max for this beam gonna occur on the left and on the right. Okay, and we have the zeta A and zeta B, and they are equal due to the symmetry. Okay. One more thing is at the maximum deflection, the slope here is 0. The same thing occur here. Okay. This is not the maximum, but the slope here is 0 because it changed. Okay. The curve just reached the peak, but this one is the peak is up. This one, the peak is downward. So you got to try to understand how the structure behave. Okay, and next, this is another kind of deflection. You may see, since the force put a lot to the light, so what happened is the deflection here is large, and the slope there is large. The slope here is small due to the force on the V is larger than on the A, and then the deformation of the curve going to be easily done, and then it's going to reach some point here, okay, with the maximum deflection, and then it's returned back like this. So there is a point here. Okay, that is not at the middle of the beam, that has the maximum deflection. And with the maximum deflection, you know that the slope here gonna be 0. So V sub C is gonna be V max, and it's occur due to the unsymmetry of the force. And you may see it's not occur at the middle of the beam. Okay, it's going to occur somewhere between the middle of the beam and the application of the force. Okay, and this one is in the opposite of the previous one. So this one, what we have is what we have. This slope is large. Okay, slope is small, and then the curve gonna be something like this. Okay, at this time, what we have is the maximum gonna be here, maximum deflection, and slope here theta is 0, the same thing. And the point of the maximum deflection gonna be between middle of the beam and the point of loading application. And we also have this before, and let's you guys to practice this. Remember, we have this, and we have the fix here, we have the roller there, and the curve gonna change from upward to concave, upward to concave downward. See, it's going to be something like this. For this one, we have the pin and the fix here, and the curve gonna be something like this. So the first one have the inflection point, and the second one have no inflection points. Okay, you can do experiment by yourself. Next, we have the indeterminate structure, and when the structure subjected to this force is going to be defect like this. Due to this support, okay, the deflection gonna be reverse back. It's gonna be revert back. Revert back for what? Revert back for C. So this portion supposed to be concave like this. So this is concave upward. This is concave downward. If the load change, okay, load change to here, the thing just change the same thing. This is gonna have the some direction like this, and it's going to return back to B. And then what we have is the B gonna defect like this. And when you reinforce this beam, the reinforcement could be different. This portion going to be mostly in the bottom. Okay, and then due to the inflection point here, okay, the steel will change to the top portion for the negative moment. And also this happen here, okay, definitely here. For this portion, it's going to be at the bottom, and for this portion, it's going to be at the top. Okay, that's a difference in the reinforcement of the beam due to the difference in the deflection of the beam. For the task, again, you also can imagine it. It's not that hard. Let's check actually. When you start the deflection, what should you do is to mark for the support is the pin. So it has theta. Okay, it have no delta. This have no delta and no delta. So there is no displacement. Okay, it can rotate. And then the second thing is the structure gonna what? Gonna move. When it's moved, it can move in vertical and horizontal direction for the truss. Okay, truss joints. Truss joint. J-O-I-N-T. Truss joint. Truss joint can move in J-O-I-N-T. In what? In vertical and in horizontal direction. Truss joint can move, okay, delta sub H and delta sub V. Okay, that means it can move downward and it can move horizontally. So this may have delta C sub V, and this is delta C sub H. And then when it's moved to here, this one gonna move to somewhere close to Y. And then you just connected the point with the straight line. It's going to be the straight line here to here. Okay, it's going to be the straight line here to here. It's going to be a straight line here to here, and it's going to be the straight line from here to here. And what we have is the shape, the deflected shape of the truss. And for this thing to be changed a little bit, let's see. Since the force is mainly applied to joint B, so the B can move. See, this can move both horizontally and vertically. So this point may move here, and this point subject to be less, right? Since the B is subjected to the force and the C have no force, so other C is supposed to be less deflection. And this one is downward. Okay, let me check. This D may move here. Okay, the bottom chord of this going to have the shape something like this. For the top chord also move. Okay, since this one move like this, it may move the same thing, and this one may move less, and the top chord will deform something like this, and the other member can deform from here to here, from here to here, and this one gonna link this one. That is the defected shape of the tusk. Okay, it's subject to the 30 kilonewton. When you draw the elastic curve, every drawing you did have their own reason. If you cannot explain why when you draw this shape, something could be wrong. Okay, and this is the result from the computer. There may be some a little bit small mistake by moving the point to the different direction. It's okay, but when you compute the result will be in negative side. Okay, and then you just take in the opposite direction, so the correction will occur. So it is natural. Even though you make the mistake, the theory will correct it by providing the negative side. That means what you assume is in opposite direction. Okay. Okay, for the frame, I did mention this before. When it's subjected to the force like this, what happens is the point A gonna move. Okay, it's not only move the frame in the vertical direction, it's also move in the horizontal direction. So this one delta sub A V, and this one gonna be delta sub A H. Okay, and when it's moved here, okay, the structure gonna move horizontally here with the delta sub A H. So when you fix this and then you sketch there, what happened is the shape of the structure will fix here and will gonna curve. Okay, point to your rigid joints. It's gonna be curved. It's not going to be smooth curve. Okay, smooth curve VE. Okay, and then when it hit this, it's going to do another simple deflection here. And since it's the right angle, since it's the rigid joint, it's going to keep the right angle here. Okay, since it's rigid joint, and then your structure will be something like this. And at the end, there is the rotation at the tip of A. Okay, and what we have is theta sub A here. So the deflection of the frame not only has the horizontal, okay, vertical, it also has the slope. Okay, the fixed support, you may see delta H equal to 0, delta V equal to 0, and slope is equal to 0. That is the result of our calculation. And rigid joint, important that when it's in normal like this, after the deflection, after the rotation, the joint still in normal angle. Okay, that is the rigid joint. That is the fixed support. There is some character of it. Okay, that is free end. They are different. Okay, the free end and the fixed support, they are opposite. Okay, this is another one. when the structure subject to this is going to be fixed, and believe me, this is going to be in this direction, and this is supposed to be here. Okay, the structure that we have may defect something like this to do curve, and then the second part, the second part of it also must be curve. Okay, and what we have is the angle here must keep in the right angle, and this one going to be curved like this. And what we have is we have the vertical delta sub c v. Sorry, that is wrong written. Okay, there's a sub c vertical, and we have this is delta sub c horizontal, and also we have this as the slope, but this time the slope measure from the direction BC, so this one is going to be theta sub c. Okay, and the same thing occur here is the rigid support. Okay, next we consider the connecting condition that I did some mention about the rigid joints. The rigid joint is something special. Rigid joints such as the fixed connected joints, such as the example here, is give an equal angle, okay, of the beam and the column after it's subjected to the force, okay, because this connection has very high rigidity. Okay, and another one is hinge joint. Hinge joint is kind of a hinge at the door. Okay, when it's subjected to the force, the angle for the rigid joint, the angle, they are equal. But for the hinge joint, the angle of the column will not equal to the angle of the beam. Because of what? Because the rigid joint has no rigidity. This is allow the deflection of the beam and the column. However, the rigid joints won't allow them freely move. And this is some example for the moment. Okay, due to the first one, they have the moment here, so it's going to change the shape like this to make them come together, and this one going to make the end in the different opposite direction, like open it. Okay, but one more thing is, no matter what they are, the angle, okay, the angle here still keep at the right angle, still be at the right angle. Okay, if you have a more complex structure, okay, especially when the frame have a horizontal force, when this one is fixed, that means there is no delta H, delta V, and theta. When this is pin, no delta H, okay, delta H is 0, of them are 0, and equal to delta V, but theta won't be 0. So that means this one won't move at all. This one be able to move, okay? And then when it's subjected to the force, what happens is the joints here move, okay? When this joint here move, the joint here also move. And now your problem is how to connect, okay? How to connect the point together. And to connect this, for sure you got to use some imagination. This one supposed to be up to this, okay, but this one will not be like this one. This one can up directly, but this one supposed to be like this first, okay, and then reverses into this. Why? Because it's fixed, Okay, it starts with different thing, and then since the rigidity of the joints, they are going to keep this one in normal angle, and this one also you got to keep it in normal angle, and then finally you will get the deformation of the beam. This is concave upward to the one that's concave downward. So the frame is a little bit much more complex when you consider it. Okay, coming to this one. This is fixed, this is fixed, this is fixed, and then the movement in the horizontal part. Oop, oop. Okay, let's have the shape there. You try to do it later. Okay, the horizontal part, and when it's moved horizontal part, what happened is you just copy the blue. You just copy this blue line, do curve into this, and into this. It's going to be the same. Okay, it's going to move here, it's going to move here, it's going to move here, and the curve just copy from the blue one. And then for the beam, just copy the not copy for the pink one. Sorry, that's for the pink. For the beam, just copying for the blue one, and then you got the curve on the top. Okay, in the shape like this one, and you got to have what inflection point. You got to make some inflection point. Okay, inflection point, and this one you have inflection point already. Okay, that's the formation of the beam. Then you may use the moment diagram to help you draw the elastic curve. Positive moment like this, that's going to have shortening or contraction. That's it, have elongation and neutral at the middle. For the negative moment, they think are in opposite. Okay, shortening, elongation, and neutral. And when you draw the reinforcement, you got to put the reinforcement. You got to put reinforcement for this. You got to put the reinforcement mainly for the RC, for the reinforced concrete. Put here. For the reinforced concrete, negative moment, you push here. Okay, for the reinforced concrete. And also, we have this before, and you can draw this by yourself, I believe it. Okay, how about this one? This one have the problem the same as before. It depends on the magnitude of M. Okay, by doing this, this is fixed. And this is negative. When this is negative, this is going to concave downwards like this. So this portion up to this, they're going to concave downward. So it's going to have the shape like this to be executed. And then the moment change to the positive. So the next one, the curve gonna be maybe like this if the M is large, or maybe like this if the M is small. And if the M is very large, the curve may be like this. It depends on the value of M relative to P. Okay. And this one also the problem that you be able to draw the elastic curve, especially from the last chapter of this theory of structure. That's the fixed, that is the P. Okay, and then you have the deflection point here, and this is negative, this is positive. So you can draw this easily. This one gonna be what? This one gonna be the same as before, concave downward, and the second part is gonna be concave upward, like this. Okay, elastic curve is not that hard if you try to do it. And then the reinforcement that you may put into this reinforced concrete beam, you may put the top on this portion, and usually you put past that's a little bit, okay, by the relation of bonding of the stick to the concrete, and this one going to be put on the bottom. Okay, And this one also, what happened is it's not that hard. They have the moment here. So moment here have what? Have support here, project here. And you also have the inflection point here. So what we have is this portion gonna be like this. And this is what? This is inflection point. So next we draw the curve. This is positive. Okay, this is negative. For a negative curve, you just put past this and then put the curve like this. And the reinforcement on this portion gonna be in the top portion. Okay, and reinforcement for the other, that's going to put in the bottom portion. So it will be like that. Okay, you got this, very similar. And for the fixed support like this, thing going to be a little bit more complex. This is going to be fixed, this is going to be fixed, and then you're going to have this is positive, this is negative, this is negative. Okay, since this one fixed, so you have to fix here, and since this one is inflection point, the point that change from positive to negative moment. Okay, so what we have, the curve of this portion going to be concave downward. This one also gonna concave downward. Theta equal to delta equal to 0. Theta equal to delta equal to 0. And the last portion is going to have the shape like this. And some important thing is at the point, since the beam is symmetry, this is going to be delta max. And the slope here, theta, going to be 0. Okay, that is the indeterminate beam. Oh, composite structure. Okay, this is going to be a little bit harder. Just makes this one fix. And what happened is, under the force, what happened is this point may move a little bit. Okay, due to the rod can what? The rod can elongate due to the force, because under the force, this one will oh sorry, let me put into this one. Okay, under the application of the force, there's supposed to be the force in the rod. Okay, this is going to have some reaction. That's reaction going to put into the rod. Okay, and then due to the rod has the pin support, the force in this going to be in the axial loaded member, what we call is two force member, and its intention, so it's going to be to have elongation. So that's why it's moved to here. Okay, when it's moved to here, this one going to move a little bit to here. Okay, and then this is fixed, and under the force, for very sure this one going to move something like this. Okay, it's kind of simple beam. Since this one is going to be fixed, so this one won't go like that. It's going to go like this to come back and taking care of this part of the beam. So they're going to go smoothly as a curve. Okay, and every point is supposed to have their own lesson. If you want to understand it, do the experiment. Okay, the curve like this. And this one also pretty hard to explain, but is what is pin. Okay, this is pin. Okay, when it's pin, delta sub x equal to 0, delta sub y equals to 0, but theta, we have theta. And then since the force push in this direction, so this point must be pushed, this point also must be put. Okay, due to this deflection, this is going to have this curve, this is going to have its curve. So if you follow that, this first portion should have the curve like this, and the second portion keep the normal angle, going to have this kind of elastic curve. Okay, you have this, push this together, and then the curve show there that rigid joints supposed to be the same, so the curve gonna be the same. See? Okay, just do a lot of practice. This also, okay, this also fixed here. This also fixed here, so this is fixed here, and this is the locker. That means this one can move. Locker is the friend of what? Of roller. And then by taking the side of the moment, okay, it will help. Okay, and if you project the inflection point, it's important because it's going to change the curve, okay, from this one to this one. So this one is B. Oops. Oh, my hand is so bad. Let me just delete it first. Okay, let me type again. It's going to have the shape like this. Okay, and it's change to what? Change to this portion. So your curve gonna be like this. Okay, and then what happened is this guy gonna take the right angle, and since this one is moved about this, I do a little bit more to move this one a little bit more too. Okay, and then we have this roller, and then we connect the graph, the elastic curve. It's called elastic curve. It's going to be something like this. So that is elastic curve for the frame. Okay, you just push this one and to get the, and I should note the picture here is not quite correct because the elastic point is supposed to be here. Deflection point is supposed to be here. And this one, oh, this one has a pin. This is also pin. This is also pin. And what happened is this is going to be curved like this. This is going to be curved in the opposite direction. And this one going to curve like this. And basis up on this, what we have is what? What we have is inflection point. You've got to draw the inflection point. That is the point that change the curve. Okay. So the first one is supposed to be something like this. Since there is no horizontal displacement and no sideway, okay, this one responds to this. And the next one, what should we have? What should we have is going to be the reverse. Okay, it's going to be reverse according to this. And next, the right angle must be kept like this. Okay, and since the line to keep like this, so your structure gonna have the elastic curve like this. Okay, that's it we have for the elastic curve. It's similar to this. Okay, that is the end of the first part of this chapter. We will going to talking about the elastic beam theory later on, and from the elastic beam theory, we will have the double integration method. For the double integration method, that we know from the mechanics of material, we will use the superposition method, the same as we have the mechanics of material for the second part. Okay, let me stop this one here.